Okay, so in the previous sections, we looked at matrices and how to perform operations with them, right? Whether we were adding them, multiplying by the scalar multiply them by a scalar, or multiply two matrices together, right? And we know the rules and when it's possible to do such a thing. So in this section, we're gonna use our knowledge of matrices and use them in an application of a type of problem that we've solved before. Right, in previous sections, we looked at solving linear systems, right? And we went over elimination, substitution methods. So here we're going to have a more kind of streamlined approach where we solve systems using matrices. Now, the first step to doing that is how do I get a system, a linear system, into a matrix? Okay, so before, our setup for our problem was something like this. So we had a type of problem that we would be asked to solve would look something like this. And then we say, all right, solve for x and y, right? And we would apply methods that we had learned. All right, so now we're going to change up how we do these type of problems. So we're going to be asked to solve these using matrices. Now, the first step I want to do when given something like this, and what this video focused on, is simply writing this as a matrix. Right? The way we do this, we're going to write it as what is called an augmented matrix. Right? So if I have this system and I want to write it as an augmented matrix, well, I would have this, right? And usually, I think in our section, they have a line here, and then they'll write the values here. So this would be an example of an augmented matrix, right? And as we can see, right, if you notice here, right, we essentially have the coefficients, right? The first column represents the column for the x variable, right? So 8 is one of the coefficients, and then 2 is the other coefficients. And we can see here y. Okay. And then here that we have that line there to represent these are what they're equal to. And here we have our constants, right? Whatever those equations are equal to. Okay, so that is how I go from a system that we're giving the system, and then we write it as a augmented matrix, right? Again, we'll get to solving it eventually, but here we just want to go strictly on how to even start the process, right? And this is our first step, writing my linear system into an augmented matrix. Okay, so now let's take a look here. Notice that the process for a 3x3 is going to be exactly the same, right? So let's say, for example, we had 6x plus 12y plus 16z is equal to 4. And then 19x minus 5y plus 37z is equal to negative 9. And here we'll have x plus 2y equals to negative 8. Okay. It's a little sloppy there, excuse me. Okay, so again here, I want to write this for now, take this system and write it as an augmented matrix. Okay, so here, all right, so the first column is going to be saved for the coefficients of my x variable. So I'll have 6, 19. Be careful here. It's kind of written like this. We're missing a variable here. So here we have an x, so that would be 1. For the y, we'll have 12, negative 5, and then here we'll have 2. Okay, and then the z coefficient 16, 37. Now here we don't have any z variables, so we do need a placeholder. So in its place, since it doesn't have that variable, we'll use the number 0. All right, and then here we'll draw a line right in our matrix here to signify that this will be this represents the equal sign, the other side of my equation. And here we'll write the constants: 4, -9, -8. All right, and again, what we have here, we have our columns that represents the coefficients of my variables, whatever I call them, right? X, Y, Z. Right, now it's standard practice here that if we have our variables named X, Y, Z, to have them in alphabetical order, starting from the left, right? X, Y, Z, and then equal to the constant. Okay, now you can change any system, or excuse, not change, you can write any system as an augmented matrix, right? Now for our particular examples here, we're only focused on if we have 3 variables, we're going to have 3 equations, but that doesn't necessarily need to be true. You can have less than 3 equations. You can have more actually as well, right? But again, those types of systems we're not going to be solving in this course. If you ever take a course in linear algebra, right, you will focus on systems that are not necessarily a square where we have whatever variables, 3, 4, whatever, you have the equal number of equations, right? But we're not bound by that. That's not a rule that needs to happen. And whatever size the system is, I can change it into an augmented matrix, and the process would be exactly the same, right? The columns would represent all the different variables that I have, right? So here I have 3 columns, so now I have 3 variables. The rows represents the number of equations. So I have 3 rows. That's how many equations I have. And if I'm told it's an augmented matrix, right, or it has that line there at the end, then I know that that last column is reserved for the constants, whatever those equations are going to be equal to. Okay.